From the street, Dubai looks untouched. Glass catches the sunrise. Concrete rises from the desert like it was poured yesterday. But the most important battle inside this skyline happens at a scale no tourist can see. Windblown sand can remove material from the outer skin. Daily heating and cooling can keep weak joints and existing cracks moving. Carbon dioxide can travel through concrete and change the chemistry, protecting the steel buried inside. None of these processes needs to destroy a tower overnight. They only need to keep working longer than the damage can remain hidden. Once corrosion opens the first crack, moisture and air gain a shorter route inward. Concrete can lose part of its grip around the reinforcement. Thermal movement can keep returning to the same injured boundary. A process that began at microscopic scale becomes an inspection and repair problem hundreds of meters above the ground. Dubai proved that monuments can be built in a desert. The harder question is how much invisible work keeps them looking untouched by it. Dubai sold the world an image of permanence. Its towers appear smooth, reflective, and new. That image is not merely architecture, it is part of the product. In 2025, Dubai recorded 19.59 million international overnight visitors, 5% more than in 2024. Many came expecting a city where every surface appears controlled, cooled, polished, and ready for a camera. That creates a quiet vulnerability. A tourism economy built around spectacular architecture does not need a structural emergency to face reputational pressure. Visible decline, recurring closures, neglected facades, or the impression of accelerated aging could turn maintenance into a tourism story. There is no evidence of such a crisis today. The risk matters because appearance has economic value. The first attacker is so ordinary that most people mistake it for dirt. Sand settles on glass. Cleaning removes it. The surface shines again. But dirt adds material to a surface. Abrasion takes material away. Laboratory studies of curtain wall glass exposed to wind-blown sand have observed cutting, impact damage, and localized deformation. Severity depends on particle size, speed, angle, exposure time, and glass properties. That does not prove every panel in Dubai is seriously worn. It proves a clean facade can still be an eroded facade. The city can wash away dust. It cannot wash back material already removed. Behind the glass, another process repeats every day. A tower is not frozen. Sunlight heats different faces at different times. Glass, metal, sealant, steel, and concrete respond to changing temperature. Joints open and close. Materials expand and contract. Engineers expect this movement. Buildings include joints and material allowances because complete rigidity would create its own damage. But that protection depends on the surrounding system remaining intact. A healthy joint accommodates movement. An aged seal may lose flexibility. Sound concrete distributes stress. Cracked concrete concentrates it. Heat should not be described as a force that makes reinforcement saw through perfect concrete every afternoon. Steel and concrete have broadly compatible thermal expansion under normal conditions. The credible danger begins after an interface is weakened. Heat does not need to create the first defect. It only needs to keep returning to it. A shrinkage crack, failed seal, corroded region, or restrained connection can become a point where movement remains active. The displacement may be tiny. The cycle still returns day after day and year after year. The key question is not whether a tower moves. It is what that movement finds at its weakest boundary. And one defense can retreat before any movement becomes visible from the street. Concrete does not protect reinforcement only by surrounding it with a thick shell. The steel also depends on the chemical environment around it. Sound concrete is highly alkaline. That condition helps maintain a passive layer on the steel surface. Carbon dioxide can change this protection through carbonation. The gas enters the pore network and reacts with alkaline components. As the reaction front advances, local alkalinity falls. The concrete may still feel hard. The column may still look clean. The steel may remain completely hidden. yet its chemical defense can be moving inward. Carbonation is not the same as corrosion. It does not prove immediate structural damage. A ReLem critical review found that moisture state, concrete microstructure, pore solution chemistry, and cover depth strongly influence whether significant corrosion follows. But carbonation can remove one defense in a hot coastal environment where humidity, salts, cracking, and construction quality may overlap. Engineers can investigate the advance using cores and indicators such as phenolphthalein. The test can reveal regions with different alkalinity. It is not a final verdict. It is a map of how far a protective condition may have retreated. The real danger appears when that front reaches reinforcement under conditions that support corrosion. Then a chemical change hidden inside an apparently solid column can begin producing a mechanical injury that finally reaches the surface. Corrosion does not need to snap a reinforcing bar to create trouble. It can first attack the concrete around it. As steel corrodes, products accumulate at the boundary between bar and concrete. Pressure can build against the cover. A fine crack forms along the reinforcement. The crack widens. The cover can delaminate or spall. The concrete placed to protect the steel is forced apart from inside. This also changes how the two materials work together. Force must transfer between reinforcement and concrete through adhesion, friction, bar ribs, and confinement. When corrosion-induced cracking grows, confinement weakens. Research has found that bond strength and bond energy tend to decline as corrosion-induced crack width increases. The bar does not suddenly slide free. The interface gradually loses its ability to grip and transfer stress. Now thermal cycling returns to the story. It acts around a boundary already changed by corrosion and cracking. The heat did not need to create the original injury. It only needed to keep the injured connection moving. This is the credible version of reinforcement separating from concrete. It is a progressive loss of confinement and bond, not a daily sawing action inside perfect material. A field study of 3 reinforced concrete structures in the Arabian Gulf, roughly 30 to 50 years old, examined cover, concrete quality, carbonation, chloride, cracking, and corrosion. Severe deterioration appeared in parts of those structures, including reinforcement corrosion and cover damage. That does not prove modern Dubai towers share the same condition. It proves harsh Gulf exposure is a real durability problem, not a cinematic invention. Now the 3 attackers have converged. Sand challenges the exterior. Heat keeps weak boundaries active. Chemistry can remove protection around steel. Corrosion then creates the crack that makes every later inspection more urgent. Finding damage sounds simple until the scale of a tower is considered. A visible crack can be photographed, but the photograph does not explain the cause. It could involve drying shrinkage, thermal restraint, corrosion, movement at a joint, construction quality, or several mechanisms acting together. A clean glass panel can be examined for pitting and scratches, but one panel does not describe an entire facade. A concrete core can reveal carbonation depth at one location, but a tower contains different orientations, moisture histories, cover depths, repair zones, and exposure conditions. An inspector is not searching for one dramatic failure. The inspector is building a map from incomplete evidence. Where is the damage? How deep is it? Is it active? Is the steel already corroding? Has the bond region been affected? Does the same condition continue above, below, or behind the tested point? Each answer creates another question about the boundary of the problem. Imagine a narrow crack discovered on an exterior column. The visible line may be only the opening chapter. An engineer must determine whether it stops near the surface, follows a reinforcing bar, admits moisture, or connects to a larger pattern on another floor. The crack may be stable. It may also be the first visible evidence of damage that began years earlier. This is why a single inspection rarely ends the story. The result must be compared with drawings, previous surveys, material records, exposure, and future measurements. Change over time can matter more than one dramatic photograph. This is where the cost of luxury changes form. The repair material may be inexpensive compared with locating the defect, reaching it safely, opening the surface, confirming the mechanism, restoring the protection, and proving where the affected zone ends. At ground level, a small repair can be routine. On a reflective facade hundreds of meters above a busy district, access becomes part of the engineering. So does timing. Repair too early, without understanding the cause, and the problem may return behind a new finish. Repair too late, and a local intervention can expand into removal, treatment, replacement, testing, and repeated monitoring. The most dangerous damage is not always the largest. It may be the small defect that remains unrecognized long enough to connect several processes. A worn surface is dismissed as dirt. A moving joint is called normal. A crack is labeled cosmetic. A carbonation front advances unseen. Then corrosion turns those separate observations into one forensic story. Dubai is exceptionally good at making complicated systems disappear behind a finished experience. Visitors see a clean lobby, a cool observation deck, and a skyline glowing at sunset. They do not see facade access schedules, sealant replacement, material testing, crack surveys, corrosion assessment, or the records needed to compare one inspection with the next. That hidden work is not evidence of failure. It is how modern cities prevent failure. The problem begins when the volume of inspection and repair grows faster than the ability to prioritize it. One scratch is trivial. One aging seal is manageable. One carbonated sample is information. One corroded bar can be repaired. Across a tower, every local finding raises a question about repetition. Across a skyline, the question becomes systemic. How many surfaces require access? How frequently must they be checked? Which buildings face the most severe exposure? Which repairs are cosmetic? Which conditions affect durability? Which warning signs remain invisible from occupied spaces? This is maintenance debt. It is not a bill created on one day. It accumulates whenever inspection is postponed, records are incomplete, protective systems age, or small defects remain unresolved. The interest is paid later through more access, more uncertainty, and a wider repair boundary. The debt can also move between building systems. A leaking joint may begin as a facade issue. Moisture can turn it into an interior finish problem. Repeated access can disrupt occupied floors. A repair planned for appearance can become a scheduling, safety, and hospitality problem. The original defect may be small, while the operational footprint becomes large. For a tourism city, that distinction matters. The record visitor scale reported for 2025 increases the value of the image being protected. Hotels, observation decks, restaurants, shopping districts, and landmark views depend on confidence in a polished urban experience. There is no evidence that material degradation has created a present tourism collapse. The risk is more subtle. If maintenance pressure becomes visible through recurring closures, stained facades, protective netting, disrupted attractions, or uncertain reopening dates, an engineering issue can become a tourism narrative quickly. One photograph of routine repair can be explained. A repeated pattern across famous locations is harder to separate from the destination brand. A city marketed through visual perfection has less room for visible aging than an ordinary city. That does not make Dubai uniquely fragile. It makes appearance part of the infrastructure it must maintain. The true luxury is not the glass. It is the capacity to inspect, clean, seal, cool, test, and repair the glass and everything behind it without interrupting the experience below. None of these processes means deterioration is inevitable at the same rate everywhere. Engineering matters. Good design can slow exposure. Dense concrete can reduce transport through the pore network. Adequate cover can increase the distance between the environment and reinforcement. Appropriate materials can improve resistance to chloride penetration. Well-designed joints can accommodate movement. Protective coatings can reduce direct exposure. Careful curing can improve concrete quality. Inspection can identify problems before they expand. Dubai also has a unified building code intended to establish minimum requirements for health, safety, welfare, environmental impact, and sustainable development. Its green building system applies mandatory requirements to covered projects and alterations. These frameworks matter because harsh conditions can be managed. But every protection has a condition. A coating only protects while it remains bonded and intact. A sealant only works while it can accommodate movement and maintain adhesion. Dense concrete only performs as intended if it was proportioned, placed, compacted, and cured properly. Cover only buys time if the specified depth exists where the steel was actually installed. An inspection only reduces risk if the right location is examined and the result leads to action. Consider the sequence after a crack is found. The surface may need to be opened. Corrosion products may need to be removed. The remaining steel may need assessment. The surrounding concrete may need treatment or replacement. The repaired boundary must then resist the same heat, moisture, salts, and movement that affected the original material. A repair is therefore not an eraser. It is a new engineered layer with its own workmanship, compatibility, and service life. Poorly matched repair material can move differently from the original concrete. A sealed surface can redirect moisture rather than eliminate it. A local patch can hide the visible symptom while corrosion continues beside it. This is why diagnosis must come before appearance. Every successful protective measure buys time. None removes the environment outside the tower. The strongest version of this story is not that Dubai defeated nature and is now being punished. It is that Dubai built a sophisticated system for negotiating with nature every day. The Skyline survives through design, regulation, inspection, maintenance, and repair. Its apparent permanence is an active achievement. Active achievements require continuous resources. The challenge becomes sharper as the building stock ages. Components installed at different times reach different stages of service life. Repairs introduce new material boundaries. Records become more important. Access demands increase. A tower can be completed within a defined project period. It must be maintained for as long as the icon remains part of the city's economic and tourism identity. Construction has an opening date. The durability does not have a finish line. Sand abrasion, thermal movement, and carbonation should not be described as one direct physical chain. A scratch on curtain wall glass does not automatically create a path to reinforcement inside a concrete column. They attack different materials and different defensive layers. Their connection appears at the level of the building and the maintenance system responsible for it. Each creates inspection demand. Each consumes access time. Each becomes more serious when protective details are weak. Each can remain small enough to dismiss until another condition makes it important. Sand can wear exposed surfaces and coatings. Thermal movement can repeatedly load joints and existing cracks. Carbonation can reduce alkalinity around buried steel. Moisture and salts can influence corrosion. Corrosion can crack cover concrete. Cracking can reduce confinement and expose new pathways. The result is not guaranteed collapse. It is a feedback problem. A defect creates a route. The route allows more exposure. Exposure creates more damage. Damage widens the repair boundary. The wider boundary demands more inspection. More inspection competes for the same time, access equipment, specialists, and budgets needed elsewhere. The system can become overloaded without any single tower experiencing a dramatic emergency. That is the uncomfortable point. Urban deterioration does not need one spectacular moment. It can emerge as thousands of small decisions about which defect is urgent and which can wait. The weakest link may not be the material with the lowest strength. It may be the defect that was never entered correctly into a record, the location that was difficult to reach, or the repair delayed because another building looked more urgent. This is how separate material problems become one urban maintenance problem. The danger is not that one grain of sand reaches a reinforcing bar. The danger is that different forces remove time from different parts of the same protective network. Dubai did not erase the desert. It created a skyline capable of resisting it through constant technical effort. That is impressive. It is also expensive, complicated, and permanent. The city can replace a panel. It can renew a seal. It can repair carbonated or chloride-affected concrete. It can treat exposed reinforcement. It can monitor cracks. It can restrict access and complete difficult work safely. The unresolved question is scale. Can every important weakness be found before it becomes a larger intervention? Can maintenance continue without damaging the seamless visitor experience the city sells? Can records, inspections, and repairs keep pace as thousands of components age under different conditions? And what happens during a period when tourism demand, operating costs, and the number of aging components all rise together? That would not automatically create a tourism crisis. It would reduce the room for error. A destination built around uninterrupted spectacle must repair itself while the audience is still watching. The skyline may appear silent. Its maintenance system never is. Dubai's towers do not need to fall for the environment to take something from them. Sand only needs to remove a little material. Heat only needs to keep returning to the same weak boundary. Carbon dioxide only needs to travel far enough to change the chemistry around steel. Corrosion only needs enough time, moisture, and access to open a crack. The skyline survives because engineers, inspectors, cleaners, contractors, and maintenance crews keep interrupting those processes. Their work is the reason slow deterioration does not automatically become failure. It is also the reason the finished city can conceal the effort required to sustain it. This video is an evidence-based analysis of documented material mechanisms, regional studies, and possible maintenance pressures. It does not claim that every tower in Dubai is damaged, unsafe, or approaching failure. It does not diagnose any named building, predict a collapse, or allege that tourism is currently in crisis. Actual conditions vary by design, age, exposure, construction quality, inspection history, and maintenance. The question is not whether Dubai can build monuments in the desert. It already has. The question is, how much continuous effort is required to keep every monument looking untouched by it? If this investigation changed the way you see Dubai's skyline, subscribe for more evidence-based stories about the hidden systems behind modern luxury cities. And tell us in the comments which layer you would investigate first: the glass, the joints, or the concrete surrounding the steel.